Hello, I have a new lecture here related to complex numbers. Before I start the lecture, let me put up my name and email address so you can copy that if you'd like to. To do this, a little background on complex numbers or imaginary numbers would be useful, but it is not essential. So if you can follow along, I think you'll find some interesting results here. Got to get rid of that. Okay, so here we go. So the question is, how do we calculate? Let me put the title back up because we have this here. How do we calculate this strange structure, I being the square root of -1, raised to the I power? I've often asked students, do they think that's an imaginary number or a real number or a complex number, which is a mixture of real and imaginary, and I get all sorts of guesses. But we're going to do the computation now, and you'll, I think, find a surprising result. So, I to the I, lots of people think it must be imaginary or at least complex. That is, some combination of real and imaginary. Turns out it's neither of these. Neither real, it's neither imaginary or complex. And we start with this famous equation. This is Euler's equation. It has some other names, but this is the name I've adopted. And what this says is that e to the I theta, where e is the natural logarithm base, is equal to the cosine of theta plus I times the sine of theta. There's lots of examples out there on the internet of computation of this, and they all rely on one thing, and that is the power series expansion of this exponential function. If you're not comfortable with series expansions and that concept, then that's fine, because we're not going to talk about it in this lecture. You can find that in many places. So the interesting thing about this is, of course, it combines the exponent property, trigonometric properties here and here, imaginary property, I, the natural logarithm, and it's not uncommon to put in values for theta to get some interesting results. These should be italicized, I think. For example, if we put in for theta here, which can be any real number, we can put in pi. And we get this. E to the I pi is equal to cosine pi plus I sine pi. That's just substituting pi in here. And this simplifies quite a bit because the sine of pi, if you remember your trig, is 0. That's here. And the cosine of pi is -1. So this famous equation becomes this even more famous equation. The trigonometric functions go away, and we get e to the I pi plus 1 equals 0, and this is famous because it combines all these iconic math symbols into one equation. It's a particularly powerful technique, and it gives us some insight in what you can do by substituting things into Euler's equation. So now let's go to the next page. Here's Euler's equation again, but this time we're going to pick a different angle. That is, theta actually refers to angles. We can talk about that in a bit. We pick in pi over 2. Once again, things simplify. E to the I pi over 2 is equal to cosine pi over 2, which happens to be, as I note here, this is equal to 0. And I times the sine over pi over 2, and sine of pi over 2 is 1, so we actually get this result. E to the pi over 2, e to the I pi over 2 equals I. So I'll ponder that for a second. Now we're going to exploit a mathematical tool that you learned in high school, which is when you can raise things to a power. And when you do, you multiply the powers. If for a common base, and you raise something to a power, you can multiply the powers. So that's what we're going to do here. We take this equation, raise it to the I power on both sides, and here's what we're looking for, I to the I. So the question is, what is this thing equal to? So we have e to the I pi over 2 raised to the I power. We multiply the powers, and we get e to the I times pi over 2. I times I is minus 1. So we get e to the minus pi over 2 is equal to I to the I. And this you can look up on your calculator. This piece right here, you can look up on a calculator. And you get 0.207. You get that this odd-looking structure we started with is actually a real number equal to 0.207 something something. Interesting. But we're not done. These are the whole basis of this is evaluating trigonometric functions. And as you may remember, trigonometric functions repeat. That is, if I take cosine of pi over 2 and add right in here, if I add pi to that and keep adding pi, this gets reevaluated. You get new values. So we're dealing with trig functions, and that allows other solutions to occur for the problem we're working on. And in fact, here are some sample angles that we could have put in to Euler's equation. And here are the results you get for e to the I times whatever angle we've listed here. So e to the I0, I times 0, is equal to 1. Right? E to the I times 2 pi is also equal to 1. And every increment here, the increments of 2 pi, we could have done this n times 2 pi for any value, any integer value of n. You keep getting 1 here. And we'll symbolize that same feature here by doing this. Pi over 2, so if we evaluate e to the I pi over 2, we get I, but we can also get additional values by doing that. If we put in pi, e to the I pi is minus 1. So now we have a process going here like this. All these are also equal to minus 1, and these are equal to minus I, and these are equal to 1. See, we're back to the starting point, and now this one is the same as this one. These are repeating. So increments like this give you this succession of values when you evaluate e to the I pi. Now, if you put in other values for the angle, just random angles, you'll get a complex number. We don't want, as I say here, we're going to avoid that. So the trigonometric functions in Euler's equations repeat, but so do these results. And we can take that into account to evaluate additional solutions for the item we started with, I to the I. So if the angle is 0 or 2 pi or these like listed here, e to the I theta is equal to these. But 1, actually all of these numbers can be represented in what I call I format. That is, 1 is equal to minus I squared. Think about it. I squared is minus 1, and we have a minus sign here, so minus times a minus that's a 1. Or I to the 4th is equal to 1. Of course, I is equal to I. Minus 1 is I squared. Minus I is I cubed. So it turns out that not only do our trigonometric functions repeat, but the representation of the result of e to the I theta also repeats this cycle where you have I to the 4th, I squared, I cubed, and you're back to I to the 4th. And this also compares with expressing these angles in units of pi over 2. So 2 pi is equal to 4 increments of pi over 2, right? 4 times pi over 2 is 2 pi. And pi over 2 is equal to 1 unit of pi over 2, and pi is equal to 2 of them, and 3 pi over 2 is 3. And you'll notice there's a 4, and there's a 4, and there's a implied 1, and there's a 1, and there's a 2, 2, 3, 3. So there's a relation between the repeating angles and the repeating expression of e to the I theta. So we can actually express e to the I times some integer units of pi over 2 this way. If you look at this for a second, you'll see that this captures what I've expressed right here. For example, if p is 2, then this piece would be 2 pi divided by 2, which is e to the I pi, and you put a 2 there, and you get I squared. And there's the 2, and there's the I squared. So this pretty little formula says for any value, integer value of p, we get this result, I to the p. All right? So here, I'm repeating that here so we can refer to it. And this increments through the 4 values that I has. Remember, those 4 values are I to the 4th, I squared, and I cubed. So I've said these things, so we're going to change our formula of the prior page and make it more general. That e to the I times p pi over 2 is equal to I times q, but q increments in steps of 4. So, for example, it is true that if we pick p equal 2, we get I squared. But if we pick p equal to 2, this result is equal to I to the 6th as well. So here, let's look at that. For any value of p on the left side, which is an integer, q can equal p plus 4, p plus 8, p plus 12, and so forth. So p can be incremented by 4, and we still get a solution to this little equation. So as I'm going to show you on the next page, p and q can take on particular values that result in these 4 different values of e to the I theta. Okay, so here are our angles. Here are the values of e to the I theta. Here are the values in I format. But the allowed values of p that produce this list is 0, 4, 8, 12 gives us I to the 4th. 1, 5, 9, 13 gives us I to the 1. I squared gives us 2, 6, 10, 14, and so forth. So now we see repeating values captured in this equation for both p, and then what does that mean for q? Q can be any of these values. Any value that p takes on can also be taken on by q. This gives us a complete description of Euler's equation and allows us to reevaluate I to the I. So we have p to the 10. Here's an example. P to the 10 and q to the 2. Let's look at that. P to the 10. Here's p. But q can be any of these. So if p is 10, q can be 2, 6, 10, 14, and so forth. If p is 12, q can be 0, 4, 8, 12, and so forth. So let's evaluate for 10 and 2. So here's the 10, which simplifies to I squared. And we can raise that to the ith power. So, right, if we put a 10 in, it's increments of pi over 2. This means we're really working with 5 pi, which is I squared. Raise that to the ith power, which means I squared gets raised to the ith power. On the left side, we have e to the minus 5 pi, because I times I is minus 1. On the right side, we have I to the I squared. So let's take a square root of both sides. And we have e to the minus 5 pi over 2 equals I to the I. This is different than the first result we got. Remember, we got something quite different. And if we evaluate this on a calculator, we get this number, which is different than what we had before. Let's go back and we'll look at the first result we got was that e to the minus pi over 2 is I to the I, and that's equal to 0.207. Now we have a new value, not pi over 2. We have 5 pi over 2 is equal to I to the I, different number. So let's improve our formalism. So here's the equation that we developed. E to the I pi over 2, I'll say it again. E to the I p pi over 2 is equal to I to the q. Take the qth root of both sides. So we got I p pi 2q, that's equal to I. Raise both sides to the I power. That's what's done here. And then here in the yellow box we have e to the minus p pi over 2q equals I to the I. So any p and its corresponding allowed q satisfies this equation. So we're going to now document what that means. And so here's a messy table. But here are values of p from 1 to 13. And here are the corresponding allowed values of q. So if p is 0, q can take on these values. If p is 7, q can be 3, 7, 11, and so forth. Now, of course, this is a list that is dictated by stopping p at 13. P can be any integer. So what we're learning now is there's an infinite number of solutions to the equation or evaluation of I to the I. So now, if we take these p's and q's and calculate p over q, because if you look at the expression we're evaluating, we have p pi 2q. So p over q is essential in these calculations. So take this table, divide each p value, which ranges to 13, by its corresponding q value, and we get these fractions. All right? 9 over 37, you get some 1 and 4/5 and so forth. Now, with that, we can calculate e to the minus p pi over 2q, because we have p over q in this table, and we know what pi and 2 are, and we can do the computation. And look at this. These in kind of a beige color, there's that 0.207 we got the first time through, but we now see it's a repeating pattern. 3 of them grouped here, 4 here, 5 here, and if you extend the table, you'd find 6 here. Here's the blues are the same color. These kind of tan things, those are the same color. So you get this very interesting pattern of solutions. All of these are solutions of I to the I. But the colored ones, the ones I've colored in boxes, those repeat. All right? So, for example, the number 0.638, right, this one, does not have a corresponding value until you go off to the far right and start looking. You probably have to go way off the table. So we now know that there's an infinite number of solutions. The smallest values are very tiny. Here's the one we calculated, 00003882. The first one we got happens to be the case for the smallest values of p and q, namely p and q both equal to 1. But we can see this table shows us the rest of the complexity. I mentioned the Euler's equation. I don't know of any solution to, or any way to prove it other than this power series thing, which is brilliant. I'll let you look at it. I'll talk a little bit about e to the ix is equal to this power series expansion for real or complex numbers. That's what Euler exploited. If you expand this out and resolve all these little squares and cubes of i's, you get this series. And then he noticed that this is one is a real number, the next one is imaginary, the next one's real, the next is imaginary, and so forth. And if you group those, you get this series plus I times this series. And this is the power series for the cosine, and this is the power series for the sine. And so you get this brilliant result. There are other solutions I've found, but they all rely on, actually one of them I found relies on using this result to prove this result, which is not very satisfactory. Another thing you see on this little page is we can evaluate the logarithm of a number like 2i, logarithm of a complex number. Sorry, a pure imaginary number. So if you have the logarithm, you can do this arithmetic and you can show that you take the logarithm, and you may remember logarithm of a product is equal to the sum of the logarithms. So the logarithm of 2i is equal to the logarithm of the real number 2 plus this business, and you get this by using Euler's equation. So the logarithm of 2i is actually a complex number. I have a quote here, a place you can go to get more details, Arfken's famous book on mathematical physics. So that's all for